Number 3, that weighted average comes out to 5.6 for number 3. No, I'm on the wrong. Sorry. Number 4 is 5.6. Number 3 is $65,000. If you missed one or both of those, you should stay and listen to the explanation. Number 3, a contractor bids on a construction project. This is also a common scenario. When contractors bid on projects, they're not guaranteed to make money, not at all. So they do calculations like this in order to submit their bid to make sure they don't go broke. There is a 0.7 probability of making $200,000 profit and a 0.3 probability of losing $250,000. So when you lose money, you lose even more money than you make when you make money, but more than double the time you're making money than you're losing money. So you really need to know what kind of deal this is before you jump into it. There's a 0.7 probability of making, so positive 200,000, and there's a 0.3 chance probability of losing, so negative 250,000. And then, we've got 10 to the 5th power here. You move the decimal 5 to the right, and then do 7 times 2. It's 1.4 times 100,000 is the way I think of it. So I move this decimal. Now that I'm 1.4, I move my decimal 1, 2, 3, 4, 5 to the right. And I get positive 140,000. And this is, I think of this as 25 times 3 is 75. But 75 tenths, so 7.5 times 10,000. And then I move this decimal 1, 2, 3, 4. But I should recognize that that's negative. So plus a negative 75,000. Okay, so that works out good to be a good deal then. I mean, on average, you're going to make if you do 100 of these jobs and everything is exactly as described, you're going to make $140,000 plus negative 70. Like sometimes you're going to make money, sometimes you're going to lose money. But when you make money, you make more money than when you lose money. On average, you make the sum of these would be positive 65,000. So on the jobs where you lose money, there's probably 2 other jobs or more where you're making money and offsets it. On average, the value is positive 65,000. Number 4, the table shows the results of a survey conducted to find out how many times a person changes jobs after age 25. So after age 25, only 1/100th or 1% of people never change their job again. Some people change their job once after age 25, 2% of the people, 1 out of 50 people. 4%, 4/100ths of the people change their job twice in their life after age 25. My memory's not great to think back that far, but I know for sure. I mean, if you're just talking about changing companies, I'm way up in the including different schools. I don't know where I am, but I'm up in the high range here for sure. All right, but if we want to find the expected number of job changes for the average person, it's an expected value calculation, or sometimes called a weighted average. The expected value is the value of 0 job changes is 0 multiplied by that probability. Of course, that will be 0, but we have to take it into account. 1 job change has a probability of 0.02. 2 job changes has a probability of 0.04 plus 3 times 0.08 plus 4 times 0.11, probability of 11%, plus 5 times 0.15 plus 6 times 0.25 plus 7 times 0.2 plus 8 times 0.09 plus 9 times 0.05. And you might wonder, why weren't we allowed to use a calculator on this? I wondered the same thing when I first glanced at it, but this is really not that hard to do. 0 times 0.01 is 0. 1 times 0.02 is 0.02. 2 times 400ths is 800ths. 3 times 800ths is 2400ths. 4 times 1100ths is 4400ths. 5 times 1500ths is 7500ths. 6 times 25, forget about the hundreds, but just 6 times 25. 4 25s is 100. 2 more 25s is another 50. So it's 150 hundredths, which is 150 ending in the hundredths place, so 1.5. 7 times 2 tenths is 14 tenths, or 1.4. 8 times 9 hundredths is 72 hundredths. And 9 times 5 hundredths is 45 hundredths. And then there's a nice opportunity, since this is a series of addition, to associate to your advantage, like this. 45 hundredths and 75 hundredths. 45 and 75 is 120. 120 hundredths is 1.20. Plus, I love adding these two, right? 2 hundredths and 8 hundredths is 10 hundredths, or 0.10. These three go nicely together because 24 hundredths and 44 hundredths is 68 hundredths, and when you add 68 to 72, you get 140 hundredths, aka 1.40. And we don't need to add the 0, because you add 0, we know the additive identity. But we do need to add this 1.5 and the 1.4. That's easy, that's 2.9. You can see now that all of the hundredths have sort of gone to 0. 2.9 plus 0.1 is 3. And 1.4 and 1.2 is 2.6. So, yeah, 5.6 is the expected value. So, right about here, right in between 5 and 6 job changes on average, which could seem wrong at first glance because it seems like the middle is right around between 4 and 5, but you see how much less likely these number of job changes are than these. There's a higher probability of a higher number of job changes, so it moves that weighted average towards that, that value that we found, 5.6.